In the today's session, we are going to discuss IR filter design. That is nothing but infinite impulse response. IR stands for infinite impulse response filter design. First, we will know, we'll discuss what is meant by IR filter. Then we will move on to how many designing methods are available for designing IR filter. Then we'll start the session. Okay. The infinite impulse response. The infinite impulse response is a type of digital filter that is used in digital signal processing applications. A filter's job, already we are very familiar about the filter's job. A filter's job is what? It will allow certain types of signals to pass and block the rest of the signals. So the infinite impulse response filter is unique because it uses feedback. It uses feedback mechanism. It requires current as well as past output data. Though they are harder to design, IR filters are computationally very efficient and very cheaper. Now we will move on to methods. Methods available for designing IR filter, infinite impulse response filter. So many methods are available. One method is called as direct method. First method is called as direct method. The second one is approximation method. Approximation of derivatives. Approximation of derivatives method. And next one, impulse invariance method. And fourth one, bilinear transformation method. And next one is approximation of fifth one, approximation of standard analog filters. Approximation of standard analog filters. Next one, spectral transformation. Spectral transformation. So these methods we are going to discuss, but mainly in out of all these six methods, mainly we are giving the concentration on bilinear transformation method. Okay. Before that, first we will know, we'll discuss infinite impulse response filter format, nothing but IR filter format. Then we'll discuss on how to solve the examples. So first topic is we will move on to infinite impulse response filter format. Infinite impulse response filter format. Okay. So what is this meaning? Now to design, in order to design IR filter, we have to express the filter, IR filter, in terms of difference equation. So if you are expressing any filter in IR filter in terms of difference equation, as we discussed in the earlier sessions, that is y of n equal to b naught into x of plus b1 into x of n minus 1 plus so on up to where bm x of n minus m. Okay, this is the what, uh, it is about the input. Similarly, minus If you are considering the output a1 coefficient term y of n minus 1 minus so on up to where minus an y of n minus capital N. It is what? It is the representation of IR filter in terms of difference equation. So if you take the transfer function for this IR filter, if you take the transfer function for this IR filter, then what happens? Taking the transfer function means rearranging terms and taking the Z transform for that. So transfer function is indicated by h of z, that is equal to y of z divided by x of z. It is the ratio of what? Output by input. Okay, it is the ratio of what? Output by input. Same thing, say if you are representing this as equation number 1, let us rearrange the terms and take the z transform. Then we are getting as uh, b naught plus b1 z to the power minus 1 plus b2 z to the power minus 2, so on. See, b naught zt of this one is x of z, this one will be taken at the denominator. Then b1 zt of this one is z to the power minus 1 x of z is taken here. Similarly goes on up to where bm z transform, this one is z to the power minus m. Yes, z to the power minus m into x of z. X of z is taken common, or all taken common, and take it to the denominator side. Divide by, coming to the output side. See, there is no first term, zeroth term. Now take the z from this one, that is 1, because see this one z of this one is y of z, correct? So we have taken the y of z common. All these terms we are taking this side, this becomes taking the y of z common. Then coefficient of y of z is what? 1 plus, see, if you take minus a1 towards this side, it becomes plus a1 zt of this one is z to the power minus 1, because y of z is taken common. Similarly a2 z to the power minus 2, so on up to where plus an and z to the power minus n. I'm going to represent as equation number 2. So this equation 2 gives the what? Transfer function of the IR filter. Now the point is, uh, what exactly these bi, nothing but b naught, b1, b2, b3, so on up to bm, what these terms indicates? Nothing but numerator terms. Generally I'm representing as bi, and at the denominator side a1, a2, a3, so on up to where an, what these terms indicates? bi and ai in general are the what? bi are the numerator and ai are the denominator coefficients. These are numerator and denominator coefficient. That's it. Coefficients. So y of z and x of z, y of z and x of z, as I told, y of z and x of z are the what? Y of z is the z transform of the output y of n, output y of n term, and x of z is the z transform of the filter input x of n. Okay. Now, to become familiar with the IR filter, we have to discuss one example. Let us take one example. With the help of an example, we'll discuss the IR filter. Okay. Now, I'm going to take one example. With the example, I'm going to discuss this IR filter, designing of IR filter. So, y of n is equal to zero point 0.2 into x of n plus zero point 0.4 into x of n minus 1 plus zero point 0.5 into y of n minus 1. It is what? It is the given IR filter. I assumed one filter in terms of difference equation. So the difference equation is given for this IR filter. Now, for this, for this filter, determine the transfer function, as well as non-zero coefficients. Already we discussed bi and ai are the coefficients, non-zero coefficients, and also determine impulse response of the filter, and also determine the impulse response of the filter. So with the help of this example, see all these three cases: finding the transfer function, first case; find the non-zero coefficient terms, second case; and find impulse response of the filter. Okay. Now, first, see here, very simple concept. Observe the given difference equation of the IR filter. Now I am going to rearrange. Okay, given, once again I am going to write given data y of n equal to 0.2 x of n plus 0.4 x of n minus 1 plus zero point 0.5 y of n minus 1. Let us represent as a equation number 1. This is the given difference equation. I am going to rearrange. Before that, the transfer function means h of z is equal to what? It is the ratio of what? Y of z by x of z. This one we know. Okay, this one we know. So as for this one, first I will rearrange the terms of equation 1 as output. I am going to take one side. Output term is there minus, if you take towards this side, it becomes minus 0.5 y of n minus 1 is equal to 0.2 x of n plus 0.4 x of n minus 1. Okay. Now from these two I will take, I will apply the z transform. Apply z transform. So what I am getting, because I have to express in terms of z domain, the transfer function is the ratio of output by input. So apply the z transform to the above equation. What happens? Y of z minus 0.5. Z transform of this one is z raised to minus 1. Y of z, y of n is divided by one time. Because of that reason, power term is minus 1. Similarly, coming to the RHS side, 0.2, the zt of x of n is x of z plus zero point 0.4 as it is z transform of x of n minus 1, one time delay, z to the power minus 1, x of z. Now here y of z is there, y of z is there. So let us take y of z as a common, 1 minus 0.5 z to the power minus 1. Okay. Similarly here I will take x of z common, x of z inside the bracket, 0.2 here left with the 0.2, here left with 0.4, z to the power minus 1. We know the transfer function is what? Y of z by x of z. So take this x of z towards this side and this term towards this side. So hence h of z is equal to y of z divided by x of z equal to what? 0.2 plus 0.4 z to the power minus 1 divided by this term, 1 minus 0.5 z to the power minus 1. So equation number 3. So what is equation 3 tells us? It is the transfer function of the given IR filter. This point is we calculated. Let us move on to the non-zero coefficient terms. Non-zero coefficient terms, let us compare with the standard for, see here, compare with the compare equation 2, b0 plus b1. Here I will write same thing. What is that? 0.2 plus 0.4 z to the power minus 1 divided by 1 minus 0.5 z to the power minus 1. This one we got correct. H of z equal to this one we got. Now compare these two equations. This one I written as a equation number what? Equation number 3 I written. So let us compare equation 2 and 3. So b not equal to what? So from this comparison we are going to write b not equal to 0.2. Okay, fine. Next, z to the power minus 1, z to the power minus 1 is the coefficient term b1. Here coefficient term is what? 0.4. Hence b1 equal to zero point 0.4. Correct? Similarly, coming to denominator, 1 1 as it is. And what about the coefficient of here? It is a1. A1 equal to what? A plus is there, a minus is there. Hence a1 equal to what? Minus 0.5. A1 equal to what? Minus 0.5. Hence, second part. This is the a part. Solution of a part, that is transfer function. B is what? Non-zero. Non-zero coefficients. Non-zero coefficients are b naught equal to 0.2, b1 equal to 0.4, and a1 equal to minus 0.5. Okay, b part is completed. Let us move on to the c part. What is the c part? Is asking for what? Find the impulse response of the system. How to find the impulse response? Impulse response is c bit. C bit is what? C bit is what? Calculation of what? Find impulse response. Find impulse response of the filter. So impulse response is represented as h of n. H of n. H of n means what? Simple. Simply we can say that, observe this one, h of z. This is what impulse response is, h of n. How we are going to calculate impulse response, h of n, taking the inverse jet transform for this one. So this is represented as equation number 3. Now I am going to take inverse jet t, inverse jet t for equation 3. Let us apply, let us apply inverse jet transform for equation number 3. What we are getting? So before that, I am once again writing the equation number 3 here. H of z equal to, for your reference, 0.2 plus 0.4 into z to the power minus 1 divided by 1 minus 0.5 z to the power minus 1. This is what? Equation number 3. Now we have to apply the inverse jet transform for this one. Before applying the inverse jet transform, I am going to split this one as h of z equal to 0.2 divided by 1 minus 0.5 z to the power minus 1 plus 0.4 z to the power minus 1 divided by 1 minus 0.5 z to the power minus 1. Now easily we can apply the inverse jet transform. Well, let us make use of definitions of inverse jet transform pair or ZT pair. We know that in signals and systems we discussed the ZT pair, a to the power n u of n. If we calculate jet transform for this one, so what we are getting? 1 divided by 1 minus a z to the power minus 1. The ROC for this one is mod of z is greater than mod of a. This is the ROC, right? This is the ROC. And similarly, one more, a to the power n minus 1 u of n minus 1. ZT pair of this one is z to the power minus 1, 1 minus a z to the power minus 1. These things already we discussed in signals and systems. Simple thing, it is ZT pair means what? If you calculate Z transform for these kind of sequences, discrete sequences, we are getting 1 divided by 1 minus a into z to the power minus 1 with ROC mod of z is greater than mod of a. Vice versa, reverse. If you take the inverse Z transform for this one, 1 divided by 1 minus a into z to the power minus 1, we are getting like this, a to the power n u of n. Now the first part of the equation number 3, or is, you can say, the transfer function. Both are things matches here. Now in place of a, what is there? In place of a, 0.5 is there. So with the reference of this formula, I am taking the inverse jet transform for equation number, so let us make 4. For equation number 4, what I am getting? Inverse jet t of this one is h of n is equal to 0.2 as it is. It is a constant term. 0.2 as it is. Okay, 0.2 is as it is. Next, then 1 divided by 1 minus, in place of a, 0.5 is there, hence it becomes 0.5 raised to what? N. N into u of n. Okay, this is the first part, plus as it is. Next, coming to the second part, see, observe, see this one. Z to the power minus 1 is there, 1 divided by 1 minus a into z to the power minus 1 is there. In place of a, 0.5 is there. 0.4 is what? It is a constant term, leave it. If it is so, the inverse Z transform of this one we are writing like this. Hence, a to the power n minus 1. In place of a, what is there? 0.5 is there. Before that, I will write constant term 0.4 as it is. Next, in place of a, 0.5 is there. Hence, a raised to what? N minus 1. So it becomes 0.5 raised to n minus 1 and u of n minus 1. Yes, this is the answer. This is the what? This is the uh, impulse response of the given filter. I'm going to represent as a equation number 5. So we, for the given filter, we assumed one filter with the difference equations, and for that filter we discussed three cases: impulse transfer function, calculation of the transfer function, and non-zero coefficients, as well as we discussed uh, impulse response of the filter. Now, from this example, we will see some points. We can conclude some points. What is first point? First point is what? Remarks. We can say remarks of this example. What are the remarks we are going to say? First remark is what? From this example, what is the first remark? The IIR filter output y of n depends not only on the current input x of n and past inputs x of n minus 1, but also on the past outputs y of n minus 1. So this remark, first remark, dependent on present, past inputs, past outputs. So what is this remark? First remark, depends current input, filter depends current input x of n, past input x of n minus 1, but also it also depends on, but also depends on what? Depends on past outputs, that is y of n minus 1. This remark we can see easily, we can see from the given difference equation, that is here. This is the IIR filter y of n. It depends on, this difference equation depends on, what is this? Current input x of n, past input x of n. X of n minus 1 means previous value, that is past. N minus 1 means past. So past input as well as past outputs. So first remark is what? Dependent. The IIR filter, the IIR filter depends on current input x of n, past inputs x of n minus 1, but also depends on past outputs y of n minus 1. So this is the first remark we can say from the given difference equation of the IIR filter. Coming to the second remark. Second remark is about the stability. It is about the stability of the filter. How we are going to check whether the filter is stable or not? The filter is stable is not, we are going to check from the ROC. Okay, since the transfer function has the denominator polynomial, since the transfer function, what is the transfer function? This one. Since the transfer function h of z has the denominator polynomial, correct, denominator polynomial, the poles of desired IIR filter, the poles means equating the denominator polynomial to the 0. The poles of a desired IIR filter must be inside the unit circle on the z plane to ensure its stability. So what it means, as per this one, I'm going to check the ROC. Mod of z is greater than what? 0.5 is what? The a equal to what? 0.5. Hence it is greater than 0.5. So it ensures a filter is said to be stable it has to, the ROC has to lies inside the unit circle. This point you have to remember. A filter is said to be stable. Its ROC has unit circle on the Z plane. Okay, IR filter must be inside the unit circle on the Z plane. Then only the filter is stable. The filter is said to be stable. And the remark third one about this example, it is about the comparison of cases. What we are going to comparison, it is about dependency, second about the stability, and third about the comparison. What we are going to compare here, compared with the finite impulse response. In the previous sessions, so many examples we discussed about FIR filter, designing of finite impulse response. FIR filters we discussed. Comparing with that FIR filter, designing of IR filter, what we are getting here, compared with the finite impulse response FIR filter, the IR filter offers a much smaller filter size. First point, from the comparison with this IR filter with FIR, comparison between IIR and FIR filter. If you compare these two filters, what we're getting, IIR filter offers a much smaller filter size. Hence, the filter operation requires a fewer number of computations, but the linear phase is not easily obtained. Hence, the higher filter is preferred when a small filter size is called for, but the application does not require a linear phase. Here, comparing with the FI filter, it offers a much smaller filter size. Hence, the filter operation requires a fewer number of computations. It is the advantage comparing with the FI filter. So the objective of IR filter design is to determine the filter numerator and denominator coefficients to satisfy filter specifications such as passband gain and stopband attenuations, as well as cutoff frequencies for the low pass, high pass, band pass, and band stop filters. So, in the beginning of the session, I told designing of IR filters, so many things are there. But in the coming session, the coming episode, in the coming session, I'm going to discuss IR filter design using BLT method. BLT method, or we can say bilinear transformation method. So many methods are available, but I'm going to give the concentration on uh, method is called as a bilinear transformation method.